So hi everyone. Today we will see a concrete analog between poset dimension and chromatic number of graphs. We will see that in this context, standard examples in poset work like Cookson graphs. So they are these trivial forcing structures driving dimension to be large. Later we will see a family of a zoo of posets. Yeah? So lots of families of posets with unbounded dimension, yet with limited size of standard examples. So that's the plan for today. And we start with a key definition, key notion in this in context of making dimension, computing dimension a coloring problem, which is the notion of alternating cycle. So let's start. So given a poset, we will often today look at its set of all incomparable pairs. So we will denote it this way, So these are all the ordered pairs, such that x is less than, not less, but incomparable with y in P. And now the first thing to do is so as we have seen, realizer is a set of linear extensions, and somewhat the target of a realizer is to reverse the incomparable pairs. So let's put a definition for it. So when we have an incomparable pair in a poset, and we have a linear extension, then we will say that L reverses xy if it happens what we expect to happen. So y is simply less than x in L. Yes, that's it. We know that in a realizer, and there must be an linear extension. A realizer, there must be an linear extension that does the job, that reverses this pair. But the linear extension can reverse more than one pair, right? And so when we have some subset of incomparable pairs, this subset is reversible. We say that I is reversible if there is a linear extension that does the job. So if there is a linear extension L of P such that L reverses everything. So L reverses xy for all xy and I. Okay. So this is the thing. And now, obviously, when only a set of incomparable pairs of a poset is not empty, so this means that simply that P is not a chain. We can put yet another, but we can just change the language for the definition of dimension, and we can say that this is a minimum. This is a minimal integer, integer d, such that the set of all incomparable pairs can be partitioned into d reversible sets. Yeah? So now instead of talking about realizers or a set of linear extensions themselves, we just partitioned a set of incomparable pairs into blocks that are reversible. So for each block, we actually have a linear extension that does the job. Okay, and now in this context, this is only useful if we have a good idea what does it mean that a subset of incomparable pairs is reversible. And here comes the notion of an ordering cycle. So the sequence of incomparable pairs, so x1, y1, maybe let's put it a sequence really, xk, yk, and now of k, and here I insist that k is obviously an integer, but it's greater or equal than 2, pairs from incomparable pairs of p. So this sequence is an alternating cycle. If the following holds, so if xi is less or equal yn plus 1 for each I in the set from 1 to k, and now I want this condition to be taken cyclically. So in particular, so this is what I mean here cyclically, and for the first time I gave you an explanation that this is so that k plus 1 coincides with 1, so literally it means that xk is less or equal than y1. Yeah? And this is obviously in P, right? Okay, so before we draw anything, let me quickly put a definition of a strict alternating cycle. So an alternating cycle and again is strict if these are the only comparabilities that we see. So if xy I less or equal yi plus yj in P holds if and only if j is equal to I plus 1. Okay. So now let's put some drawings. So what is a two cycle? Well, this is x1, y1 incomparable, x2, y2. Right? So x1 is supposed to be below y1, and x2, y2, and x2 is supposed to be below y1. Yes. For the three cycle, yeah, x1 is supposed to be below y2, x2 below y3, and x3 below y1. Yeah. So this is an alternating cycle of size 2. In short, two cycle is a free cycle. Now, if these are the only comparabilities, right, then this is a strict alternating cycle. So possibly in an alternating cycle we allow, for example, this, yes? This is fine, yeah? But if you want it to be strict, then a relation between x and y is exactly described by this matching, yeah? Going to shifted elements. And you can see that actually in a strict alternating cycle, the set of x's form an antichain and the set of y's form an antichain. And you should also be aware that some of these elements can coincide. So xi can coincide with yi plus 1. Yes? In theory, all of them could coincide, and then we just have a one big antichain. Yes? So that's the picture of alternating cycles. And now, why are we talking about them? Well, there is a proposition. The proposition is that when P is a poset, and I is a subset of the comparable pairs, then the following conditions are equivalent. So, point 1, I is reversible. Point 2, I contains no alternating cycle. And point 3, I does not contain strict alternating cycle. Okay, so that is an ultimate answer to the question posed a moment ago. What does it mean that a set of incomparable pairs is reversible? Yeah, what is an obstacle? So that is the ultimate obstacle, existence of an alternating cycle within the set. So let's prove it. Okay. So three conditions are equivalent. Let's have a look. So I implies II. Well, suppose the opposite. Suppose so that I contains an alternating cycle. And let it be x1, y1 up to some xk, yk. And let's also, since I is reversible, take this linear extension that is witnessing it. Take L to be a linear extension of P, reversing all pairs in I. And now immediately you see that something goes wrong. So taking any pair xi, yi, we know that L reverses the pair. So we know that yi is less than xy in L, right? But now this is an alternating cycle, so xi is below yi plus 1. And this is in the poset. So in particular it must be in the linear extension. So we have this in L, and this holds independently of the choice of I, so it holds cyclically, yeah? For all I, cyclically. Well, this cannot hold, right? You cannot have y1 strictly below y2, which is strictly below y3, which is strictly below yk, which is yet again strictly below y1. Yeah? That's a contradiction. And this way we prove that there is no alternating cycle in a reversible set. Okay, let's move on. Let's have a look at 2 implies 3. Well, it's trivial. Okay, so all the work now is to see that that 3 implies 1. So we have a set of incomparable pairs that does not contain a strict alternating cycle, and we want to show that it can be reversed. So let's do something brutal, yeah? Consider a transitive closure of what you want to do. So you want to take a poset P, and you want to reverse pairs in I. So you want to take I, the dual of I, yes? So the dual of some set here is that it just contains yx whenever xy is in I, yes? That's the dual of a relation. So we want to consider a transitive closure of this set, yes? So something like this, yeah? So now the claim is actually that it's still a poset, so that it's acyclic, yes? If this is true, then we will take a linear extension of it, and we will have a linear extension of P that respects ID, so reverses all the pairs in I. So claim is that it is acyclic, so transitive of P union ID is acyclic. Okay. So let's prove it, and let's suppose otherwise, right? So now, if we suppose otherwise, we have a cycle. We have a cycle here. What does it mean? We have a cycle, so we have elements from our poset, and then sometimes we see a poset relation marked as a white arrow, and sometimes we see this extra relation. This is a relation from ID, yes? Yeah? So we can have stuff like this, yeah? And we suppose that the cycle is closed. Yeah? incredibly. So what do I want to note here? So that's a relation P, that's a relation ID. I wanted to take minimal, but let's not think about it right now. What I want you to observe is that there are at least 2 red arrows in the cycle. This is because, well, there must be a red arrow because otherwise we are just in P and P is a cyclic. One red arrow doesn't suffice because there is always a linear extension that reverses a fixed pair. Yeah, so if you force the relation to fix some pair, to reverse some pair yx, this is still a cyclic because we know that there is a linear extension of P reversing that single pair.
A single one is implied by transitivity. It's not incomparable.
A single one, if there is one red arrow, how would you argue that it's like that it's okay, that there is no cycle like this? How would you argue?
By transitivity.
So by transitivity, you have that this element is below this element, so they are not incomparable. Of course. Okay, so this is yet another reason that we see at least 2 arrows, yeah? At least 2 red arrows. Okay. Now let's have a look. What do we see? So take some red arrow and let's call this one x1. Yes. Now you go along the white arrows, and the other element we call y2. Yeah. Now along the red arrow we have x2, which actually is coinciding in this case with y3. Yeah. And then we have x4, which is x3. I'm sorry. Apologies. x3, which is below y4 in the poster, as witnessed by these edges. And this is x4, which is below y1. So I claim that we see here an alternating cycle, right? And this alternating cycle is on pairs of I. Yes? So you see, x1, y1 are incomparable, and x1, y1 is an I, because y1, x1 is an ID. Yeah? x1 is below y2. y2, x2 is, x2, y2 is an I. Yeah, x2 is below y3. And so on. And this goes cyclically. So we do have an alternating cycle. We started with an assumption that, of item 3, so that we have no strict alternating cycle. Well, you can very quickly see that if you have an alternating cycle, then there is the perhaps smaller strict alternating cycle. You can also directly in this proof take a cycle which is shortest, so you don't have any extra edges flowing around, and this will be a strict alternating cycle, which gives you a contradiction, and this contradiction is with the fact that we suppose that this is acyclic. So we suppose that this is not acyclic, yeah? So this is acyclic, and if it's acyclic, then we consider L linear extension of this thing, transitive closure of P union ID. So 2 things to observe. First, that L is a linear extension of P itself, because it extends even more than P, so it extends P in particular. And second is that L reverses all pairs in ID. Yeah, and this is again because L is a linear extension of ID itself. Yeah, so it respects ID, so it reverses pairs reverses all pairs in I because it respects ID. Okay, so that completes the proof. of if that 3 implies 1, so it completes the proof of our proposition. So now we know that being reversible exactly means that we have no alternating cycle in the set. And this is a nice combinatorial property, and this is actually the engine below that is responsible for all the graph coloring business in this topic. So let's have a look at the example how the alternating cycles can be useful computing dimension. Okay. So here's our example. Let G be a connected graph. On at least 2 vertices. Now we will discuss a poset. So we are forming the poset P where X is so the base of the poset is just a set of all connected induced subgraphs of G. And we have a relation H1 less or equal H2 in P if the subgraphs. So our relation is a containment relation. So if the H1 is simply contained as a subgraph in H2, yeah. So that's a poset. We start with your favorite graph and do this. You result in a poset. Clearly, it's a partial order because containment gives you a partial order relation. And then what we want to observe about it is that the dimension of this poset is equal to a very specific number, which is the number of non-cut vertices in G. Okay? Okay, so let's take a look. Let's prove this statement here. Let's first start distinguishing our set of non-cut vertices. A vertex is non-cut. A cut vertex is a vertex such that when you move it from a graph, it gets disconnected. Yeah, you have at least 2 connected components. We started with a connected graph. So here is the set of all our non-cut vertices. All non-cut vertices in G. Now we are working on we are proving that something is equal, so we need to prove 2 inequalities. Let's look at the easier one. So look, if we have at least 2 elements, then dimension is at least 2. And this is simply because, well, you can take these 2 elements as singletons, yes? And then clearly there is no relation between them. These subgraphs do not contain each other, so this forms an antichain in our poset. So and this antichain is at least 2, so the dimension is at least 2. It's not 1. Yeah. So that is the only little observation I needed, because the rest will rely on the fact that t is larger. So if t is at least 3, then what we do is to consider a subposet, the subposet Q of P, taken induced by singletons, so the one element subgraphs that are just the cut vertices, yeah? So x1, yeah, as a subgraph, yeah, xn, and their complements. So like g minus x1 up to g minus xn. Okay? So here I'm using that t is at least 3 to notice that all these graphs here, specifically at the bottom line, they are distinct, yes? So if you were to imagine a case of yeah, if there will be two vertices, then possibly when you remove one, you get only the other, so some vertices here would coincide. But if t is greater or equal than 3, then we really have like 2n elements, 2n subgraphs, distinct subgraphs of our graph G. And when you look at the containment relation, you discover quickly here a standard example. Yeah? So x1 is contained in everything, so it's a standard example flipped over, yeah? The only thing that it's not contained in it's the complement, yeah? And this is true for all. So this means that the Q is isomorphic to standard example Sn, and which drives the dimension of our poset P to be at least n. Okay, and that is for the lower bound. Now our goal will be to prove the upper bound, so that dimension of P is most n. So, what do we do? Well, we want to show that dimension is bounded. What we're going to do is we're going to partition the set of incomparable pairs of our poset into blocks. Each block will be reversible. Okay. So, here are the blocks. So for I from 1 to n, let Si be the pairs, incomparable pairs in our poset, such that now the distance from the vertex xi in the graph G, distance in G, to graph H1 is less than the distance of xi to H2. Yeah? So we have vertices x1 to xn. When we look at the vertex xi, and we take an incomparable pair, so we take two subgraphs, maybe xi is closer to one of them. If xi is closer to h1, then h1, h2 ends in si. Okay? And now, okay, so that's some family of sets, S1 to Sn. There are two things to be proven. One is that each Si is reversible. Second is that this family covers the incongruable pairs of our poset. So let's move on. Claim 1. Si is reversible. And here we will work with alternating cycles, yes? So suppose otherwise. Suppose it's not reversible. And let H1, let's take some other letter, K1 up to KK is an alternating cycle. Be an alternating cycle. With all pairs so contained in Si. Yeah? So what will be the problem with that? So, what is the problem with that? Well, take some J, yeah. So Hj, Kj is a pair in Si, yes? This means that by definition, the distance of xi to hj is less than the distance of xi to kj, distance in g. Now, okay, we need to think about this alternating cycle. So if that was hj and that was kj, yes, then hj is below kj plus 1 and kj is above hj minus 1, yes? And I think I want to go to hj minus 1. So what does it mean that hj minus 1 is below kj in the poset? Well, this means by definition that hj minus 1 is contained in kj as a subgraph. There's two subgraphs of G. This means that if we consider distance of xi to the graph hj minus 1, we are taking a subgraph of this graph, so the distance can only get larger, yeah? It doesn't get smaller. And here is our contradiction, yes? Because we started from nj, and we get a strict inequality that the distance of xi to hj is less than the distance of xi to hj minus 1. This cannot hold cyclically. So, so that's a contradiction. It's a contradiction with the fact that we suppose otherwise. We suppose that we have an alternating cycle. So we don't have this alternating cycle. So Si is reversible. Let's move to the second claim. Sm cover the whole set of incomparable pairs of P. Yes. So let's argue about that. Let's consider some incomparable pair, HK. Yeah. So now we should take the right vertex. H is incomparable to K in. So this in particular means that there exists a vertex, let's call it X, such that it's, well, let's try. It's in VH, but it's not in VK, yes? There must be such vertex, otherwise they would be comparable. So what can we say about it? Let's take this vertex. So case 1, X is non-cut. Well, if X is a non-cut vertex, then this means that it has a number, yeah, say xi. Then we claim that this pair is an Si, yes? And this is pretty obvious because the distance of xi to h is 0, and xi is not in K, so it's non-zero. So indeed, then hk is in Si. So we are left with the case that X is a cut vertex. Of G. So let's try to draw some conclusion here. So imagine that this is our X, and the graph somehow is disconnected, yeah, when we remove it. So X is in H minus K. X is not in K. So if we think about K, right, the subgraph K, it must be, it is connected, so it must be in some component of G minus X, right? So let's imagine that case is here. And now what I want to look at with you is any other component. There are at least two components, so I want to look at the component that doesn't contain K. Yeah? And now, if you consider this component, the only thing we need is that there is a non-cut vertex of the whole graph in this component. And this is, it took me a minute to actually verify this claim, but this is pretty cool, I think. What you should look at is like you take this component together with X, it's connected, so take a spanning tree of it, yeah? And consider a leaf of that spanning tree. This vertex for sure is non-cut, yeah? Because if you remove it, the remaining stuff is connected there. So that's the reason that there exists Y that is non-cut here. And here is here. Yeah? So this Y then has a number, this number is xi, and now if you look at xi, and you think about the distance of xi to h and k, you realize that you're in good position, because any path from xi to k has to walk through x, and x is in h. So it is closer to h than to k. So hk again is in Si as desired. So indeed, for any incomparable pair, we can find block. We can find it somewhere in the covering. It might be that it's in more than one, so that's why it's a covering. It doesn't have to be a partition, but it's even better for us, right? Okay, so that closes our example, and now. I want you to go with me to this concrete parallel between posets dimension and chromatic number of graphs. is not a chain, so we have incomparable pairs. And now let's put a hypergraph on this poset, yeah? And the vertices of the hypergraph, I want them to be incomparable pairs of our poset. And now edges of our hypergraph, I want them to be alternate cycles. Okay? Now, it's quite immediate to see that that when we get the proper coloring of a hypergraph, the number of colors is actually bounding dimension. So what is the proper coloring here? It's pretty obvious. A vertex coloring of a hypergraph is proper if there is no monochromatic edge. Now, given that, we should immediately see together that dimension of a poset is actually equal to the chromatic number of its hypergraph. Chromatic number obviously is the least number of colors, so that you can properly color it. Yeah, so imagine that you color this hypergraph with k colors, then when you look at a single color, it's a proper coloring, so there is no edge completely on these vertices. No edge means no alternating cycle by our definition. So this means that these vertices, which correspond to incomparable pairs, they are actually reversible. Yeah? So for each color, you can find a linear extension in the poset that reverses corresponding incomparable pairs. So indeed, the k coloring gives us a dimension of most k, and vice versa. The same algorithm, it's the same thing. So, okay, so that's nice. Have a look what happens if we have a standard example. So let's look at the standard example of size 4, say. Yeah. So this is A1, B1. This is A4, B4. Yeah. So this is the type of relations that we see here, right? Yeah, quite dense. But now if we look at the hypergraph of it, in particular there we have 4 incomparable pairs that corresponds to our A1, B1, yeah, A2, B2, A3, B3, and A4, B4. And now, if you look at any 2 pairs there, what do you see, yes? So take, for example, A2, B2 and A4, B4. What do you see? A2 is below B4 and A4 is below B2. That's a 2 cycle. What does it mean? Well, it means that we have edges here in this hypergraph, edges of size 2. So this is quite a good notion of a clique for our hypergraph. So if we define this clique number conveniently like that, then we immediately get that the standard example number of a poset is the clique number of our hypergraph. Now, the standard example number is the size of the largest standard example in the poset. Well, if there is a standard example, if there are no standard examples, let me remind you, are of size of these 2, then we put it as 1, yes? And then that's it, right? So, so here you can see that indeed, this is a somewhat trivial forcing structure. Standard example is set for dimension, yeah? We know that if you find it, dimension is monotone and undertaking subposets. So, so indeed, it drives dimension to be large, but it's somewhat the trivial forcing structure. Yeah, and as with graphs, it is natural to wonder if there is some other way to force dimension to be large. Yeah, and like the triangle-free graphs, yeah, that have arbitrary large chromatic number. And indeed, in posets, we have a whole zoo of examples, and this is the topic of our next little section here. Let's jump into it. And let's see how dimensions can be large, but the standard examples are not large in the poset. So that's our section 3.2. Yeah. We do know that there are posets of arbitrarily large dimension, but if I remember correctly, all our examples were large just because there was a standard example in it. Like including our last example here with the subgraphs, connected subgraphs. I think all the way through, we never seen how can we make dimension large without it. So let's see immediately. Let's consider incidence posets. So what is an incidence poset? It is a poset that is a result of some operator put on graphs. So take a graph G and then make it a poset IG, incidence poset of G as follows. So elements of our poset are vertices of G and edges of G. You can change some, yeah? And now V is less than E in our poset IG if and only if V is a vertex, E is an edge, and V is incident to E. In G, right? So, yeah, what does it look like? So let's take, I don't know, K4. So you know what is K4, right? Again, that's K4, right? So when we think about IK4, we have 4 vertices, so 4 minimal elements, and 6 edges, yeah? So, yeah, and then we have an edge here, and we have an edge here, right? That's incidence poset of K4. So it turns out that dimension of these posets, incidence posets of quicks, grow when n grows, and this is the subject of our next proposition. So dimension of IKN is omega log n. It grows with n. And actually this is the right asymptotics, but we will leave it as some exercise perhaps. Why it is yet interesting? Well, because because we don't see large standard examples here. That's quite obvious. This is just because the degree of the vertices at the top is at most 2. So you can have S3, I think, yeah? IK3 gives you S3, I believe, right? Because you have 3 vertices and then you have, right? Yeah, that is a standard example of size 3, right? But you don't get the standard example of size 4 here. So if G is a graph, then I of G, standard example of I of G number is at most 3. Yes? And yet we can have large dimension. Okay, so let's put our hands on the lower one here. So let's take a realizer for I, K, N. So consider L1 to LD, the realizer of the poset I, K, N, yes? So our goal is to show that D must be large. And then, so let's take these vertices of Kn, let's call them like V1, obviously V1 is equal to M. And now, by the Erdős-Szekeres, we can find a subset of the vertices. So there is V2, a subset of V1. V2 is not too small, so we give up something, but we have at least square root n elements. And V2 is somewhat behaves uniformly, you could say, perhaps, with respect to 2 of our linear extensions. Yeah. So when you look at L1 and L2, then you see basically the same order after taking dual. So, and the vertices in V2 are ordered the same in L1 and L2 after taking dual. Yeah, so I guess you can think of it like this is your linear extension L1, you have all the n elements here. Well, okay, you know, when you take a linear extension of this, there are vertices and there are edges. They are all mixed up here, right? But here I just consider, for this statement, I consider what is the order of the vertices, yeah? Since the vertices of the graph given form an antichain in the incidence poset, we can have an arbitrary permutation here. So we have L1 and we have L2, and considering the vertices, the V1, we can have our 2 arbitrary permutations. But now Erdős-Szekeres gives us that we can filter out and find square root n subset, so large, still a large subset, such that the order of the vertices is the same after taking dual. So perhaps you have here A, B, C, D chosen, and maybe you again have here A, B, C, D, or maybe you have D, C, B, A. Yeah, that's 2 options you can have. Okay, so that's the step, and now we just iterate it, yeah? So if you iterate, then at the very end, you find out some VD, which is a subset of V1, yeah? And this VD will have still a lower bound on the sides, which is n to the 1 over 2 to the power of d minus 1 steps, so to the power of d minus 1, yeah? And vertices in VD are ordered the same in L1 up to LD after taking dual. Yeah? So again, if we imagine that VD is some red subset of vertices, yeah? And then we look just at our linear extensions here. Yeah, V1 up to Vd. Yeah, then we look at the red subset, which is somewhere here, possibly in different spots, right? But then when we read them off, we always read the same sequence or the dual of it. Or is the sequence being reversed? Okay, so this is what we do. And now, given that Vd still consists of some elements, actually we need 3, we'll get a contradiction. So if Vd has at least 3 elements, then what do we do? Well, then let's look at these elements. Yeah. Let's choose 3 of them. 1, 2, 3. 1, 2, 3, yes? Let's call them. So this is A, B, C. So perhaps here we also see A, B, C. And here perhaps we see C, B, A, yes? And here again maybe we see A, B, C, yes? That's our position here. A, B, C is in Vd, and then A is less than B is less than C in Li, or C is less than B is less than A in Li for each I. Yeah, from a set from 1 to D. Okay. Well, this is a problem, and this is an immediate contradiction, because now when we look back to our position of the poset, yeah, we do have these vertices. Let's just look at A and C. Yeah, we have B somewhere, whatever, it can be here. And then we have an edge between A and C, yeah, that's an AC edge. It's an edge in the graph, yeah, because that was a click after all. So now, what I want to observe with you is that edge, let's give it a name, C. Where is C, yeah, in our linear extensions? Well, let's make it green, yes? This is a green element. It is here. So where is it? Well, these are linear extensions after all, so they have to respect the poset, so green must be always above A and C. So if this is A, B, C, it must be somewhere here, right? And if it's CBA, it must be somewhere here. So the conclusion I want to make here is that for each I, we have that B is less than C in Li. And that is an ultimate problem, because B is incomparable to C in the poset we talked about, IPN. So this is not a realizer. Yeah, because we have no linear extension in the realizer that puts green below this red. That's a contradiction. Contradiction with what? Well, it's a contradiction with the fact that Vd has at least 3 elements. Okay. But this gives us immediately the bound. Well, and what do we have? We know then that this is, so the size of Vd, yeah, is at most 2, right? But we know that this is lower bounded by these applications of Herder-Sekadech, so this is n to the 1, 2 to the d minus 1, yes? So when we put the logarithm, yeah, so the logarithm of 2 is 1, right? And this should be greater than equal than 1 over 2 to the d minus 1 times logarithm of n. yeah, which gives us that log n is at most 2 to the t minus 1. So if we take another logarithm, we get that t is greater or equal than log n minus 1 plus 1, yes? So this is what we claimed. Actually, we didn't need this omega, right? We could put a nice looking function there. So this concludes the proof. Okay. Let's move on. Let's look at another animal in the zoo. Okay. So now we will talk about interval orders. So for interval orders, there is a specific one, obviously somewhat universal to the family of universal interval orders, and this makes sense to just look at them. So by universal interval order, of order n, now this n, let it be at least 2 to avoid some nonsense, is the poset un such that the elements are intervals, right? So these are intervals ij, such that both endpoints are in natural numbers, and these natural numbers are between 1 and n, yeah? And we don't like degenerate ones, so we insist that I is strictly less than j, and that's our family of intervals we look at. And then obviously ij, like an interval order, yeah, is less than kl in our business, if and only if j is less than k. So this less sign, well, together with these closed brackets here, actually indicate that we talk about closed intervals here, which is more handy in this context, but it doesn't change the game. The universal order on open intervals is as well as large dimension, but somewhat it's nice to have them closed here. So okay, so our proposition here is as simple as that the dimension grows, yeah. Dimension of un is at least log n. Now, first, let me point out that again here we will have large dimension without our forcing structures, without standard examples. And this is simply because interval orders, as you might have recalled, know by now, are exactly the 2 plus 2 free orders. Posets, yeah? So what is a 2 plus 2? 2 plus 2 is a structure like this. But if you like, you can draw it like this. well, this is just a standard example on size 2, and we don't have it. So, yeah, so this is even more striking, right? Because over there with incidence posets, we didn't have large standard examples, but we could have standard examples of size 3. Now we don't even have standard examples of size 2. So we are down to the most ridiculous case. And still we can have large dimension. Okay, so let's try to see this one here. So in order to get it smoothly, we need to know a chromatic number of a specific family of graphs, which are shift graphs and generalized shift graphs. So let's go there quickly. So this is a kind of intermezzo here. The shift graph Gn, so of order, say again, some order n, is the graph this time, with vertices being again our pairs. So such that ij are natural. So you can think of them as these intervals we had a moment ago, yeah? So I strictly less than j, so the same set of objects, but now edges are exactly when ij and jk is adjacent to jk, for all I less than j less than k is equal m at least 1, yes? So what is our business here? Well, when we look at the axes, yeah? So here is number 1, here is number n. Our vertices again are pairs, so you can think of them as kind of intervals here, right? So this could be an interval ij. And what is it adjacent with? Well, it's adjacent with all the intervals with the left endpoint here, yeah? And all the intervals with the right endpoint here. That's the graph we see on these intervals. Now, this is a fun fact, actually. There are many jokes about it, how much in the kindergarten you should be to know it. That the chromatic number of Gn grows in n and actually is at least log n. It's at least ceiling of log n, and this is actually the correct number. We will see it again as some exercise, I guess. So let's quickly argue that this is true. So how do we do it? So we should consider a k-coloring of Gn. Consider phi, a proper coloring, yeah? A proper k-coloring, yeah? So something that uses k-colors and properly color our object. We want to again show that k is large, yeah? So now, given that, look at our axis, yeah? And then fix some index I, which is from 1 to n. And when you look at I, observe what are the colors of the intervals that are being being finished at I, so with the right endpoint at I, yeah? Call this set xi, yeah? So let xi be the set of alphas, yeah, from our k coloring, yeah, so from 1 to k, such that there exists I prime less than I, such that the color of I prime I, yeah, so the color of one of these guys is equal alpha. Yeah, that's the set. And now the thing we need to observe here is that, so this is our small claim here, that given that I is distinct in J, we have that xi distinct from xj? Well, let's just have a look, yeah? Take I, take j, yeah? We have some set of colors seen here, xi, and some set of colors seen here, xj. Why are they different? Well, just look at the interval ij. It has some color beta. And beta definitely, from the definition, is in xj. Is it in xi? Well, not. Why? Because we have a proper coloring, and if we allow beta to happen here, we have two vertices adjacent in the graph with the same color. That's not an option. So beta is in xj and beta is not in xi, so they are indeed different. Okay, so that's indeed true. And now we can count, right? Because what is the situation? We have n coordinates, and on each coordinate we have a set, and all these sets are pairwise distinct. These sets are subsets of our k colors. So we have 2 to the k possibilities, and we have to fill in n coordinates. So it must be that 2 to the k is greater than n, which means that log n is greater than k, but k is the number of colors, so we can put a ceiling here, if you like. And that proves our fun fact. Well, we have to stay with this business for a moment, because what we actually need is the chromatic number of the double shift graph. So let's quickly define it. The double shift graph let's call it Gn. Now let's put a number 3 here, and we could put a number 2 here. Yeah, that indicates that we have pairs, and now we have triples. So Gn3 is the graph such that its vertices, yeah, are now triples, yeah. So these are I, j, k, such that all 3 are naturals, and 1 is less or equal I is strictly less than j, is strictly less than k, is less or equal n. That's the vertices. And now 2 vertices are adjacent if the suffix of size 2 coincides with the prefix of size 2. So ijk is adjacent to jkl, are adjacent for all, well, again, for all these numbers. Yeah? Okay, so now if we think about the situation, what we see is are these triples, so we can mark them as this. Yeah, this is I, j, k. And now this triple is adjacent to the red triple, because red triple looks like this. Yeah, and this is L, JKL. Yeah? So that's our graph. And another fun fact is that the chromatic number of Gn3 is at least log n. Yeah? Okay, let's argue that quickly. So so in order to prove it, we take a coloring again. So let consider again phi proper k coloring of Gn3. And now let's define subsets with 2 indices, one less than the other. And now when we think about xij, we look at the ith index, we look at the jth index, and we consider all the triples with last two elements being I and j. Yeah? And we collect the colors, right? Yeah? We collect all the colors of the triples being yellow on my picture. Yeah? So xij is a family of alphas. Alpha is from 1 to k, such that there exists I prime that the phi of I prime I j is equal alpha. That's the set. Okay, and now the claim we need is that if you think about the mapping C that starts from ij and gives it xij, that this is a proper coloring of the original shift graph. Yeah? So we put something on pairs. Yeah? And we claim that this is proper in the GN2. So we went down from GN3 to GN2. Why is it so? Well, look at the I, J, and look at J, K. Yeah? I less than J less than K. Yeah? And now, what do we see here? We have I and J, yeah, and we have the set xij, and these will be the green ones here. You know, we collect all the colors of the green ones. Yeah, that's the xij. Now we have jk. Right? So we take the xjk. So now we want to collect all the blue ones, yeah? So stuff like here, yeah, or like here, right? That's the blue ones. So ij and jk are adjacent, are two vertices adjacent in GN2. So in order to prove that we have a proper coloring, we need to show that the colors are different. Yeah? Well, why are they different? Xjk contains a guy which is ijk. Yeah, it's a color under what? Under phi. It's a color ijk. Yeah? This color is here, of this interval. Now, can it be an xij? Not really, because if this alpha is also in xij, this means that there is an interval here, again with color alpha, with the two last elements being here. But then this guy and this guy would be adjacent in the original graph GN3. But we started with the proper coloring of GN3. So this guy is not in xij. So xij is indeed this thing, so xjk. So we have that the coloring is proper. Okay, so since the coloring is proper, we can conclude because of what? Yes, because we discussed the coloring of GN2 the number of colors we use is the number of subsets, is bounded by the number of subsets of the initial colors. We used k colors, so we have at most 2 to the k, and we have bounded that 2 to the k is at most the chromatic number of GM2. This is what we proved. But GM2 is, the chromatic number is lower bounded by log n. So this means that log n lower bounds k as desired. Okay. So with this stuff, we are ready to get back to the proposition that the dimension of the universal integral graph of order n grows like log n. Yes. Okay. So proof of the proposition. Yeah. So consider a realizer, and one may be a realizer of UN. Yeah? And now consider a triple ijk, yeah? So with these numbers being as you expect. Yeah? So remember, recall that in our business here, we discussed about intervals, closed intervals, yeah? So ij is an object, is an element in our poset. And jk is also an element in our poset. And ij is incomparable with jk, right? In mu n, right? So since it is like that, and we have a realizer, there is a linear extension here, such that it puts jk below ij. Yeah? So given ijk, choose alpha, which is from 1 to d, such that jk is less than ij in L alpha. Yeah? Okay. Well, let it be that for this choice we make that this is phi, and we put that phi of a triple is equal our choice alpha. This allows me to write in a concise way what I want, which is that phi is a proper coloring of GN3. Okay, let's look what happens. So we need to take two vertices from GN3 that are adjacent, and we need to show that they have distinct colors. Yeah. So we take ijk and we take jkl. Yeah, they are vertices of G and 3. They are adjacent, yeah? Adjacent. Yeah, we do have this, that 1 is less or equal I, less than j, less than k, less than l, less than equal n. Okay, so let's see what is happening here. I, j, k, l. So, suppose that phi of ijk equals phi to jkl equals some alpha. Yeah? Now, what does it mean? Well, if you take ij and you take jk, then from the fact that phi ijk is alpha, we know that jk is less than ij in an alpha. But we also know that that jkl, phi of jkl is alpha. So that means that kl is before jk in an alpha. kl is before jk in an alpha. Do you see a problem with that? There is a clear problem. Well, kl is actually above ij in the poset. Yeah? This is ij, this is kl. This interval is completely yeah, there is even an emission. So that's a contradiction because L alpha should be a linear extension, so it should respect UL, but it doesn't. The contradiction is with the fact that we suppose that two adjacent elements in GM3 receive the same color, which means that they have distinct colors, so indeed the coloring is proper. And since the coloring is proper, we can see how many colors we use, and the number of colors is from 1 to d, yes? So this means that d upper bounds the actual chromatic number of GM3, but this we know from the fun fact that this is at least log n, as desired. Okay, we continue next week with another animals in the zoo. So far so good, thank you.